Hello dear audiences, this is the Statistic and Probability for Engineers, the episode 8, and I am Mohammad Momizadeh, the presenter of this lecture. So today we want to talk about the Bayes rule at the end of the day after a long advertising about the properties and applications of a Bayes rule. Today we try to talk about the total probability and also the Bayes rule. And if we have a time at this lecture, we will catch a point on the random variable and we will discuss about the probability distribution function at the end. So let us start our discussion by the last definition. At the beginning we just start our discussion by one example for the multiplicative rule. Indeed, that multiplicative rule is the basis for the Bayes rule, and we just promise at the last lecture to show one example about the multiplicative rule as well again. So this is the question, and here we go. A coin is biased so that a head is twice as likely to occur as a tail. So means that this coin is not fair. I have a shape of a coin over here, and as you know, most of the coin that you know from the reality are unbiased, but this coin is unfair, and a probability of occurring head is not as the same as probability of occurring tail. So if the coin is tossed 3 times, in the question they ask you to find the probability of getting 2 tails and 1 head. I'm looking for this probability. So in any question that is given to you, it's very important to understand the question and clearly prepare the situation for the sample space. Over here the coin tossed 3 times, so first of all, before that we're going forward, we need to talk about the situation by sketching the tree diagram. As you can see over here, I sketched the tree diagram to determine the situation. If it's tossed more than 3 times, it's impractical to sketch the tree diagram and write all the elements of the sample space, but over here it's easy to write it. So in the first toss, as you can see, in the first toss we have the head and tail. In the second toss, after that we just do that one, we have the head and tail for each case, and again head and tail. So by sketching the tree diagram, you can easily write the elements of your sample space. Means that the first one in each branch you can find 1 sample point. So we have H means that the first toss is head, the second toss is head, the third one is head as well. And also we have HT at the second branch. That means the first one is head, the second one is head, and the last one is tail. So in this way we can write all the sample points in 1 sample space. And when I just wrote it over there, I'm looking for getting 2 tails and 1 head. I'm looking for this probability. So I select all cases that contains 2 tails and 1 head. I circle that cases and I wrote over here as a subset of that sample space, or as an event of A. So up to this point, if the coin is unbiased and the coin is fair, the probability can be easily calculated. It's going to be 3 cases out of 8 cases, so it's going to be 3 over 8. But over here the coin is biased. We should talk about this case. I emphasize about that. The probability will be the number of the elements over the number of sample space if all cases over here has the same chances to be occurred based on a probability axiom. And over here, because the coin is biased, then this cannot be happen. So what shall we do? We first of all calculate the probability of head and tail separately. What do I mean? Let us take a look over here. We have this situation. So here I highlight one sentence of this question, that a coin is biased so that a head is twice as likely to occur as a tail. So if we toss a coin only 1 time, then we have only two possibility. The head is occurred or tail is occurred. I mean, there is no other cases. Because of that, in one tossing of a coin, the head and tail are the only sample points of that sample space. Since the probability of sample space is equal to 1 based on axioms of the probability, then the probability of head plus probability of tail should be equal to 1. And based on this information which is given at the question, which a coin is biased, that a head or the probability of head over here is twice as likely, means that it's going to be 2 times of a probability of tail. So right now we have a system of the equation. You learn this type of the things at the linear algebra. Clearly, this is the system of the equation of two variables. One pH, the another one is pt, like x and y. And to solve this simple linear equation, it's only need to replace the probability of head by 2 times of probability of t. If I replace the second equation in the first equation, then I have 2 times of a probability of t plus probability of t or tail equal to 1, and from this equation I can find the probability of tail. So if it's equal to 1, then simply you can say that the probability of t, 3 times of probability of t, is equal to 1, or probability of t is equal to 1 over 3. So in this case I found the probability of tail, which is 1 over 3, and based on a second equation that the probability of head or pH is equal to 2 times of probability of t, it should be 2 times of 1 over 3 or 2 over 3. So I found the probability of head and tail separately if we have only one toss. Right now I should calculate the probability of an event A. As you can see, probability of A is as the same as follow. So over here the probability of an event A means that getting 2 tails is a probability of TTH or HTT or THT. So in each of these cases we have a union between them. When we have a probability of union, I said that it can be happen this one, or I emphasize about that words that I use it, means that this one, or because of that we have a union. So when we have a union, we can use the additive rule to calculate the probability, and the probability of the union is the addition of the probability if the events are independent. And as you can see, TTH, HTT and THT, all of them are independent. They are totally actually independent from each other, and it's going to be the addition of each. And when we talk about the probability of TTH, for instance, let me just write it over here that what's happened in this middle. So we have the extension of this formula. I try to extend the formula. When we talk about the probability of TTH, means that the first one should be tail, the second one should be tail, and the third one should be H. Means that I use a word and over here. And when I use the and over here, means that we have the intersection. So we have the intersection of T1, T2 and H3. For the remains we have the same thing. And right now when we have the intersection of some events, we should apply the multiplicative rule. And since these probabilities, these events are independent, we can write the intersection of the probability as a multiplication of them. So means that I can multiply them and write it as a multiplication. At the end of the day, by calculating the value, we reach to the value of 2 over 9. And as you can see, it's totally different from 3 over 8, where the coin is unbiased. So finally we reach to the Bayes rule, and let us take a look at the Bayes rule. But before that one, we should talk about the theorem of total probability. The Bayes rule totally related to this theorem. So if as you can see over here, if the events b1 up to bk constitute a partition of a sample space S. What does it mean? It's a partition. For being a partition, we have two conditions. As you can see over here, I just put the condition for being a partition for S. First of all, the events that we talk about, it should be mutually exclusive, in the meaning of there is no intersection between the pair of the event bi and bj for I and j for different values of I and j should be empty. As you can see over here, this is b1, this set, and b2 and b3, and all of these three sets that I determined over here are totally disjoint. There is no intersection between b1, b2 and b3. And the second one, it should cover the entire space, means that the union of these sets should be equal to the space, the sample space. And as you can see again over here, the b1 union by b2 union by b3 is equal to S. In this case, we can say that b1, b2 and b3, the sequences of these events, indeed determine a partition for S. If this situation holds true, means that if the b1, b2 and b3 or b1 up to bk are the partition for the space, for this condition that I just circle on it, then we can say that for non-empty sets, for any event A of S, if we have one event over there which has an intersection with them, the probability of that event is a summation of the probability of bi and that given set, and at the end it's equal to this value. But how can we reach to this formula? Indeed, in a previous examples we calculate this formula. So at the beginning we started by A as an event, so this event also can be partitionated to three parts. I can write it as A intersected by B1, this purple color determine that part. As you can see over here, this purple part is A intersected by B1, the blue part is A intersected by B2, and the last part, the color, the light brown colors, determine the A intersected by B3. And the set A or the event A can be calculated as a union of these three partitions. So we can rewrite A as A intersected by B1 union by A intersected by B2 union by A intersected by B3. And if we have more partitions like B4, B5 up to BK, this holds true over there as well. So right now the probability of that event A is as the same as probability of these three unions. So based on additive rule, if we have union of the set, then it's going to be the addition of the probability if this type of the sets are disjoint or mutually exclusive. Since they are mutually exclusive over here, it's a partition and they are mutually exclusive, then there is no intersection between these three sets. Means that between the purple, blue and that light brown color there is no intersection, so we don't need to subtract the value of their intersection from them. So because of that we can say that it's an addition of these three probabilities. And we have the intersection of two sets in each probability. So because of that we can use the multiplicative rule, and again we can rewrite them as a probability of one of them. For instance, for the first one is a probability of B1 times probability of the second one A, in a condition that the B1 has been given. So it's true for the remaining parts, and if I just summarize this summation by one symbol, then I reach to that formula. This determines the total probability. We need to calculate the probability of an event A as an addition of the probabilities, and it's written based on a condition of A and BI, as you can see at the end. So now let us take a look at the Bayes rule theorem, the original case of that one. Previously, based on our discussion, we realized that the probability of A can be written by this expression, means that we could write the probability of A by partitionate the events of A to three parts as the following: probability of B1 times probability of A in a condition of B1, and so on. Or we can rewrite it as a summation of probability of BI times probability of A in a condition of BI. Right now, if I choose one specific actually events or partition of S like B2, the probability of B2 in a condition of A can be rewrite over here by using the conditional probability. If you remember that we had a formula for the conditional probability, and instead of that condition we changed that condition to the intersection of a set, and we divided by the probability of the second one, which is probability of A. Right now, instead of this probability of A at the denominator, I replace that value of a total probability which we calculated previously. And instead of the numerator that we had the probability of B2 intersected by A, I would write that one as a probability of B2, but the probability of the first one times the probability of the second one, A, in a condition of first, which is a multiplicative rule, which is determined by the multiplicative rule. This is the form of the Bayes rule. But really, if you just take a look over here, you realize one fact, that indeed when we have a conditional probability like B2 in a condition of A, and we want to calculate the probability of some conditional cases like this, by swapping the place of the conditional probability when the given set, the given events is the partition for the space, by swapping their places we can use the actually Bayes rule. As you can see, this part at the numerator is one cases of the probability of A at the denominator. By the other words, this one is repeatedly occurred at the denominator, and we will write for all partition to calculate the Bayes rule. Right now we will take a look at some example to see that how the Bayes rule works. Now let us look at the first example for the Bayes rule. So the question is as follows. A group consists of 60% of girl students and 40% of boy students. 20% of boy students and 50% of girl students are Cypriot. So if I just split the space based on a gender, then we have 60% of girls that we denoted by B1 over here at the shape, and 40% boy students that we denote them by B2 by that event. And right now we have one event that the given event is being Cypriot. And for this reason we have 20% of boy students, so the probability of being the Cypriot and being boy is 0.2, and 50% of girl students are Cypriot, so the probability will be 0.5 for being Cypriot and being girl. If a student is taken at random from this group, means that we select a random student from this group, then for this person we have a question, and the question is as follows. What is the probability that the given student is Cypriot? So means that I'm looking for the probability of A, and for finding the probability of A that we denoted at the example by C over here, we should calculate the total probability, means that it's gonna be the probability of being boy times probability being Cypriot if in a condition that the given person is boy, plus probability of being girl times probability of being Cypriot given that the person is girl. So if you remember that, we just have this actually condition, means that probability of A in a shape that we have it over there is equal to the union of two sets, means that it's a probability of A intersected by B1 based on the shape that we have it, union by the probability of the event of A intersected by B2. And since the given sets are totally disjoint or mutually exclusive, and indeed they are the partition for the given space, we can use the additive rule. Then it's going to be the probability of the first one plus probability of the second one, and based on a multiplicative rule we can rewrite them by the given formula, and by calculating the values and multiply them, it's going to be 0.38. I can use that one for the second part. Means that if a random selected student from this group is Cypriot, means that one information is given, it's already done, means that the condition is being Cypriot and it's given over here. I'm looking for the probability that this student is a girl, means that I'm looking for the probability of being girl if the given student is Cypriot. So I just put this actually expression at the denominator, this expression at the denominator. So if I put it at the denominator, at the numerator I just select one part of that one, means that I just divide a part of that which is probability of being actually girl over there, because they asked for this part. We just put this part at the numerator. So this calculation leads us to this formula, and we can calculate it. It's going to be 0.79. By the another words, I multiply the corresponding values. So 0.5 multiplied by 0.6 and 0.2 multiplied by 0.4. So I added them together to calculate the total probability. To calculate the total probability, we should do that one. With more examples, you can see the magic of this formula, the Bayes rule. Normally we use this rule, the Bayes rule, for calculating a lot of interesting things. You will see more example over here right now. So over here you have one example that is the routine example for the Bayes rule. I mean, normally we just give this example for the application of the Bayes rule. Over here we just talk about the manufacturer that produce a goods or the products with 3 machines, and this is the percentage of making that type of the products. If I consider the sample space as all products of that manufacturer, then we can divide or partitionate that one to 3 parts. One part made by the machine 1, one part by the machine 2, and one part that is made by the machine 3. So the percentage of each is given as follow. The machine 1 made 20%, so the probability of making by the first machine is 0.2, for the second machine is 0.3, and the remaining one, which is 0.5, are made by the last machine. So these are the probability of making the products of that manufacturer. So the events that we consider it in the middle of this story is a defective product. So this defective product, let me just make the machine 1 by M1 and choose the symbol of M2 for the second machine, and for the last one we choose the M3 to denote it over there. Right now the defective part for the first machine is 0.3. It's given respectively by that value 0.3. The probability of getting defective by the second machine is 0.1, and for the last one is 0.2. If I want to know that what is the probability that the given or selected by the random product be the defective, then we should multiply the corresponding values. Means that we should multiply these values together to find what is the defective probability. This is a total probability that we have it. We can avoid to write the formula and write it like this, but totally we can write that the probability of getting the defective value will be equal to the multiplication of corresponding values. Means that it's going to be 0.3 multiplied by the corresponding value over there, which is equal to 0.2, and we do the remaining things as well. So as I said it before, by multiplying the corresponding values we can find the probability of the or being defective product. So if you want to know what is the reason that we can use this formula to calculate the probability of detective cases, you can see over here that the events D can be written as a union of the intersection of D by the partitions, and because it's a union, so we can use the additive rule. And if I use the additive rule with that information, which the partitions over here M1, M2 and M3 has no intersection, I can rewrite them as the addition of the probability, and at the end of the day, this is the multiplicative rule which lead us to that formula. Right now, in the second part of the question, they said that if the sample is defective, means that one information is given, it has been already done that the given sample is defective, then they ask you to find the probability that the defective cases made by the second machine, means that we are looking for the probability of M2 where given that the cases, the product is defective. Indeed, we have a value of swapping case, means that we know the probability of being defective if it's made by the second machine is 0.1. It's given by the question as well. So, but I need the inverse cases. I want to swap the place of the condition over here. So to calculate this value, simply you can divide the value of M2, the corresponding value by of M2, over the whole values that we have it. By the other words, if I just consider whole cases that is equal to this part, if I just put it at the denominator, then I should select the part which is belonging to the second machine, means that this part, and I should write it at the numerator. This is gonna be the value. Or by the calculating the value over there, we can put the formula as well. The formula is as follows, means that it will be the total probability which we calculated over here. We put the formula over here before. At the denominator we should put this value, and at the numerator of that fraction I should put the corresponding part of the second machine, means that I should put this part, which is the second part of the machine, at the numerator. So with that calculation we can find the probability of M2 in a condition of D. So let us take a look at another example. So next, let us take a look at the application of Bayes' rule in biology or some related things in biostatistics. However, it's out of the scale of this course, but it's not a bad idea to take a look at the different example. So it's about the sensitivity and specificity of the test. And what does it mean? Let us take a look on it. So over here we have one type of the disease that is split in a population, and as you can see, the people who has a disease are selected over here, and who has not the disease. So we just I just circle the concept over here. So based on a question, the prevalence of the disease in the population is 1%, and this prevalence means that 1% of a population, or 0.01, affected by the disease and has that disease, and 0.99 is a probability of has not the disease over there. So we have the partition for the population that we can divide it to two parts. One part that has a disease with the probability of 0.99, and one part who has disease with the probability of 0.01 based on this information. Two more things are given in the question. One is a sensitivity and the another one is a specificity. So sensitivity is defined as a true positive rate, means that if the person over here we have the case over there, so if the person has the positive disease, means that has a disease, and also the test is positive for that one, it's going to be sensitivity. And specificity is a true negative rate, means that if the test is negative for that person and also that person has no disease, then it's determined that thing. So it's a false part of the test, means that, for example, in a corona times we have one test that determine the situation that if the person has a disease or not, but this test was not that much accurate. So meticulously, when we discuss about the test, this test can be positive but the person has not a disease, or this test can be negative where the person has a disease. So these two things can be determined by these two parameters, sensitivity and specificity. So the first part, the question we ask you to find the specificity of that disease. What does it mean? We want to calculate the probability that a person who tests negative, means that this one is given. We know that the person tests over there and the person has get the negative test, and I want to know that how much that test is accurate, means that we want to know that if the test is negative, then what is the probability that the person does not have the disease, means that we are looking for this probability. If the test is negative, this negation sign at the back of T determine the negative test. If the person get the negative test, I want to know what is the probability that the person has not a disease. So I partitionate the space to two parts. The person has a disease determined by D, and negation of D determine the people who has not the disease. And based on the information which is given in the question, it's the rate is 1%, the rate of prevalence of disease. So means that 0.99 is a probability of have nothing the disease, and 0.01 is a probability of having the disease. So over here, to calculate the probability of not D in a condition of not T, means that the test is negative. I want to know what is the probability that the person has not a disease. To calculate this one, I just know the swapping case. What does it mean, the swapping case? The swapping case is a case that the probability of has not the disease and the probability of getting negative disease, means that it's an accurate accuracy of the test, and it's a true negative rate indeed, means that we know the inverse case of this one, where the test is when the person has no disease, and the probability of the negative test, we know this part, and by knowing this we want to calculate the inverse case. So the probability of knowing that the person has not a disease and the test is negative is a true negative rate, or a specificity of that test, which is 95%, and the probability of that one will be 0.95. So the important part of solving the Bayes rule question is understanding the sample space, the partition for the sample space, and the event that we want to talk about it. So over here we want to know about the negative test, the people who get the negative test, and for the people who has not the disease, this one is 0.95. I mean, this is the accuracy of that test. And for the people who has a disease, if we want to know what is the probability of not getting the test, I mean we get the negative test, is a false negative rate, and it's equal to 1 minus sensitivity. which is 1 minus 0.9, and 0.1 is a number. Right now, by clearing the situation, the corresponding number should be multiplied and add them together to calculate the total probability. Means that the probability of this case, the denominator determine the probability of negative test. The probability of getting the negative test is equal to this expression. Means that the probability of getting negative test, given that the person has a disease, times the probability of being disease, times plus the probability of getting a negative test if the people has not a disease, times the probability of has not any disease. So this value can be calculated by the following expression, and the result is 0.99 approximately. Means that the accuracy of this test is 0.99. So we are looking at another example that is given in a website of Math is Fun. So it's an example of picnic day. It's a nice example to understand how can we interpret the happening of daily routines to calculate some complicated things or calculate some magical things. So we are planning to have a picnic today, but the morning is cloudy. So we have three facts over here that is a routine facts that you can get it. It's given that 50% of all rainy days start off cloudy. So this can be interpreted by this probability. Means that the first fact can be written like this. The first fact determines the probability of being cloudy, the probability of being cloudy. If let me just use the C alphabet to determine the cloudy and R alphabet to determine the rainy. So 50% of all rainy days means that we have already announced that the day are rainy, means that the rain is happen already. The probability of being cloudy in a rainy days is given by 0.5 or 50%. So the first fact or the first expression that is given is a probability of being cloudy if we know that the day is rainy. So this is the first fact that is given over here. The second one said that but cloudy morning are common. It's only about being cloudy, means that the probability of cloudy days is given. The second fact determine the probability of cloudy days, which is equal to 0.4. So this is the second fact that is given over here, 0.4. So the another things that is given at the question, it's about the dry months over here. Means that usually it's a dry month and 3 out of 30 days tends to be rainy, or 10% of the months are rainy. So it's give you the rainy days probability. So the third fact that we have it is a probability of rainy days. So first of all, when some information are given in the question, it's better to determine the meaning of that expressions. So when you just write the correct extract of that information, then you have already solved the question. You know what is the information inside of the question. So as you can see, the probability of being rainy is 0.1. Based on that information, they ask you a question, and what is the chance of rain during the day is the question that we have it over here. So means that this day at the beginning they said that it's cloudy. So means that I'm looking for the probability of getting rain if I know that the day is cloudy. So based on a Bayes rule theorem, it will be it's very simple to calculate this probability. So if you just take a look on this probability, let me just shift it over here. So if you have these things, if you want to know that what is the probability of have a rain if the day is cloudy, so we know what is the probability of being cloudy if the rain is happen. It's given at the first part of the question. So because it's a conditional probability, it will be the probability of their intersection, means that R being rainy and being cloudy over the second one, or the probability of being cloudy. So we know what is the probability of being cloudy. It's given at the question. You don't need to calculate it by the total probability. This probability of being cloudy is given by the second statement over here. Means that it's in a comment that the day is cloudy and it's equal to 0.4. So I substitute 0.4 instead of the probability of being cloudy. But for the intersection of these two probability, I can use the multiplicative rule, and because the probability of being rainy is given, I will start it by the probability of being rainy. Means that P of R, the probability of raining, multiplied by the probability of being cloudy if the rainy day is given. So means that I just swap, somehow we swap the place of the condition by these techniques. So if you just take a look on it, the probability of being cloudy if it's rainy already is 0.5. It's given at the question 0.5, so I can replace it by 0.5. And the probability of getting rain is 0.1. So by calculating that expression, you will find it as 0.125. So means that 12.5% we have a chance of rain if the day is cloudy. So as you can see, by having some information about the situation, you can easily do some magic and calculate some difficult things based on the given information at the question. And that's the reason when we said that if the situation is totally magical. So as I said before, it's the magic of the Bayes rule. Indeed, for the big data, when a lot of data are available, this Bayes rule can do really the magic. Means that for general cases, if we have the probability of one thing in a given condition, means that, for example, if I have the probability of an event A given that the B has been occurred, then it's easily can be calculated when the swapping case is given. Means that this is the key of the Bayes rule. Means that when we have the inverse part, means that when we have the probability of B where the A is given, then easily we can calculate the probability of A when B is given. This is the key of the Bayes rule theorem. So it means that at the end of the day, we can calculate the things that we have it over there by the multiplicator by conditional probability. Means that we divide it by the probability of B, and the numerator of that one, that expression should be their intersection. So because we have the probability of B in a condition of A, it's only need to multiply that terms by the probability of A. Means that in one side of the story that we have it for the Bayes rule theorem, if I just sketch it in one table, in one side of the story, this is what do we need? We need the probability of A in a condition that the B is given. And other side of the story, we need to know the probability of A, probability of B, and the inverse of that conditional things. Means that if we have the information on the right side, we can get the information of a left easily. So if we know the swapping place of them, means that the probability of B in a condition of A is given. In a data analysis, we use this concept severally, and there are a lot of sophisticated situations that can be interpreted by the Bayes rule. And as much as you get expert in these things, and you can use it in a tree diagrams as well, you can use it in a probability of the big data, and there are a lot of application of a Bayes rule in this region. So I will finish the lecture today, and in the next lecture we will start our discussion by using the random variables, and we will discuss about the probability distribution function in a discrete and continuous cases, and that situation we will discuss about the integral and summation for addition of the probabilities. Thank you for your attention.